A 600-watt 230-volt one-phase gate motor will not work properly with a 208-volt power supply. Electric motors are designed to operate at a specific voltage and frequency. The power drawn by the motor is determined by the voltage supplied and the current flowing through the motor. With insufficient voltage, 208 volts instead of 230 volts, the motor will receive less power than it was designed for. This will result in reduced torque and speed. The motor may overheat and fail prematurely due to increased current draw. The 10% rule allows for a 10% deviation from the nominal voltage for short-term operation. However, this rule applies to lighting circuits, not motors. Using a 600-watt 230-volt gate motor with a 208-volt power supply will likely lead to the following problems. Firstly, reduced gate opening and closing speed. Secondly, increased risk of motor overheating and failure. And thirdly, shortened lifespan of the motor. To ensure proper operation, it is crucial to use a motor that is designed for the voltage available in your power supply. The motor's voltage rating must match the supply voltage within an acceptable tolerance. Running a 230-volt motor on 208 volts can have several negative consequences. The motor will experience reduced torque, making it difficult to start or operate under load. It will also experience reduced speed, affecting the gate's opening and closing time. The motor will draw more current to compensate for the lower voltage, leading to overheating. Overheating can damage the motor windings and insulation, ultimately causing premature failure. The motor's lifespan will be significantly shortened due to the increased stress and heat. It is important to avoid using a 230-volt motor on a 208-volt supply. Doing so can lead to costly repairs or replacements. There are a couple of options for properly operating the gate motor. Firstly, replace the motor with a 208-volt motor. This is the ideal solution, ensuring the motor operates within its design parameters. Ensure the new motor has the same horsepower or wattage rating as the old motor to maintain proper gate operation. Secondly, use a step-up transformer. A step-up transformer will increase the 208-volt supply to 230 volts, providing the motor with the correct voltage. Choose a transformer with a wattage rating that is at least 25% higher than the motor's wattage to accommodate starting surges. Install the transformer close to the motor to minimize voltage drop. When selecting a motor, always check the voltage rating on the motor's nameplate. The nameplate also provides information on the motor's horsepower, current draw, and other important specifications. Ensure that the motor's voltage rating matches the voltage of the power supply. If the motor's voltage rating does not match the power supply voltage, do not attempt to use it. Doing so can damage the motor and create a safety hazard. When using a transformer, ensure that it is properly grounded. Grounding protects against electrical shock and reduces the risk of equipment damage. Follow the manufacturer's instructions for grounding the transformer. Use appropriately sized wiring for both the motor and the transformer. Undersized wiring can cause voltage drop and overheating. Refer to the National Electrical Code, NEC Table 310.15 for proper wire sizing based on the current draw and length of the circuit. Ensure that all electrical connections are tight and secure. These connections can cause arcing and overheating, which can lead to fires. Use a torque wrench to tighten connections to the manufacturer's specifications. Regularly inspect the motor, transformer, and wiring for any signs of damage. Look for cracked insulation, loose connections, and signs of overheating. If any damage is found, repair or replace the affected components immediately. Keep the motor clean and free of debris. Dirt and debris can accumulate on the motor windings, causing overheating and reduced performance. Use a vacuum cleaner or compressed air to remove dirt and debris. Avoid using water or solvents to clean the motor, as these can damage the windings. If you are not comfortable working with electricity, hire a qualified electrician. Electricity can be dangerous, and it is important to take precautions to avoid electrical shock. An electrician can properly install and maintain the motor and transformer, ensuring safe and reliable operation. When working with electricity, always turn off the power at the circuit breaker. This will prevent electrical shock. Use a voltage tester to verify that the power is off before working on any electrical component. Wear appropriate personal protective equipment, PPE, such as safety glasses and gloves. Safety glasses will protect your eyes from flying debris, and gloves will protect your hands from electrical shock. Follow all applicable electrical codes and regulations. The NEC provides detailed requirements for electrical installations. Ensure that your installation complies with all applicable codes and regulations. Before replacing a motor, consider the motor's efficiency. A more efficient motor will use less energy, saving you money on your electricity bill. Look for motors with a high efficiency rating, such as nano-premium efficiency. A motor operating at a lower voltage than it is designed for can experience several issues related to its magnetic field. The magnetic field strength in a motor is directly related to the voltage applied to the windings. When the voltage is reduced, the magnetic field becomes weaker. A weaker magnetic field results in reduced torque production. Torque is the rotational force that the motor exerts, and it is essential for starting and running the load. With less torque, the motor may struggle to start or maintain speed, especially under load. The motor's efficiency is also affected by the weaker magnetic field. The motor's efficiency is a measure of how much of the electrical energy it consumes is converted into mechanical energy. A weaker magnetic field reduces the motor's ability to convert electrical energy into mechanical energy, resulting in lower efficiency. This means the motor will consume more power to produce the same amount of work. Lower efficiency leads to increased energy consumption and higher electricity bills. The current draw increases in response to the weaker magnetic field. To maintain the same power output, the motor will draw more current from the power supply. This increased current can overload the motor windings and cause them to overheat. Overheating can damage the insulation and eventually lead to motor failure. The motor's slip, the difference between the synchronous speed and the rotor speed, can also increase. Increased slip can further reduce the motor's efficiency and increase the current draw. The motor's power factor, the ratio of real power to apparent power, can be negatively affected. A lower power factor means the motor is less efficient at using the supplied power, leading to higher energy consumption. All these factors combine to create a less efficient, less reliable, and potentially dangerous operating condition for the motor. It is essential to operate motors within their specified voltage range to ensure optimal performance and longevity. In situations where the supply voltage is consistently lower than the motor's rated voltage, using a step-up transformer or replacing the motor with one that is compatible with the available voltage is highly recommended. The 10% rule is often misunderstood and misapplied, especially when it comes to electric motors. While it is true that electrical systems can often tolerate slight voltage variations, the 10% rule is generally intended for lighting circuits and other resistive loads, not inductive loads like motors. The rule essentially states that a voltage drop of up to 10% is acceptable under normal operating conditions. This means that if a circuit is designed for 120 volts, a voltage drop down to 108 volts, 120 volts minus 10% of 120 volts might be acceptable. However, this does not mean that equipment will operate optimally or even safely at the lower voltage. For lighting circuits, a slight voltage drop may only result in a dimmer light output. The effect on the performance and lifespan of the lighting is usually minimal. However, motors are much more sensitive to voltage variations. Motors require a specific voltage range to operate efficiently and safely. When the voltage drops below the motor's rated voltage, the motor's performance can be significantly affected. The motor may experience reduced torque, reduced speed, increased current draw, and overheating. These problems can lead to premature motor failure and safety hazards. The 10% rule does not account for the specific requirements of motors. It is a general guideline for voltage drop in electrical systems, not a universal allowance for undervolting equipment. Motors should always be operated within their specified voltage range to ensure optimal performance and longevity. The NEC provides guidelines for voltage drop in branch circuits and feeders. NEC Section 210.19. One informational note number 4 recommends that the voltage drop on branch circuits should not exceed 3% at the farthest outlet of power, heating, and lighting loads or combinations of these. Furthermore, the maximum voltage drop on both branch circuits and feeders combined should not exceed 5%. These recommendations are intended to ensure that equipment operates efficiently and safely. It is important to note that these are recommendations, not mandatory requirements. However, following these recommendations can help to prevent voltage drop problems and ensure optimal performance of electrical equipment. The actual acceptable voltage variation for a motor depends on the motor's design and application. Some motors are designed to tolerate a wider voltage range than others. However, it is always best to operate motors within their specified voltage range to ensure optimal performance and longevity. When in doubt, consult the motor manufacturer's specifications or a qualified electrician. A motor's nameplate provides critical information about the motor's operating characteristics, including its voltage rating. It is essential to understand and adhere to the information on the nameplate to ensure proper operation and prevent damage to the motor. The nameplate voltage indicates the voltage at which the motor is designed to operate. It is typically expressed as a single voltage, such as 230 volts, or a range of voltages, such as 208 to 230 volts. The nameplate frequency indicates the frequency of the alternating current, AC, power supply that the motor is designed to operate on. It is typically expressed in Hz, HC, such as 60 Hz. The nameplate horsepower, HP, indicates the mechanical power that the motor can produce. It is a measure of the motor's ability to perform work. The nameplate current, in amps, indicates the amount of current that the motor will draw when operating at its rated voltage, frequency, and horsepower. The nameplate speed, in revolutions per minute, RPM, indicates the speed at which the motor's shaft will rotate when operating at its rated voltage, frequency, and horsepower. The nameplate service factor, SF, indicates the amount of overload that the motor can handle for a short period of time without overheating. A service factor of 1.0 means that the motor can operate continuously at its rated horsepower. A service factor greater than 1.0 means that the motor can handle a temporary overload. The nameplate insulation class indicates the temperature rating of the motor's insulation system. The insulation class is expressed as a letter such as A, B, F, or H. Each letter corresponds to a maximum allowable operating temperature. The nameplate enclosure type indicates the type of enclosure that the motor has. The enclosure protects the motor from environmental factors such as dust, moisture, and corrosion. Common enclosure types include open drip proof, OP, totally enclosed fan-cooled, TEFC, and explosion proof. The nameplate also includes other information such as the motor's model number, serial number, and manufacturer's name. It is important to consult the motor's nameplate before installing or operating the motor. The information on the nameplate will help you to ensure that the motor is operated within its design parameters. If the motor is operated outside of its design parameters, it can be damaged. It is important to consider the motor's starting torque requirements when selecting a motor for a particular application. Starting torque is the amount of torque that the motor can produce when it is starting from a standstill. Some applications, such as those involving heavy loads or high inertia, require motors with high starting torque. Other applications, such as those involving light loads or low inertia, can use motors with lower starting torque. There are several different types of motors, each with its own starting torque characteristics. Induction motors are the most common type of motor. They typically have moderate starting torque. Synchronous motors have high starting torque, but they require a special starting mechanism. Direct current DC motors have very high starting torque, but they require a DC power supply. The type of motor selected should be based on the starting torque requirements of the application. If the motor does not have enough starting torque, it will not be able to start the load. This can damage the motor and the equipment that it is driving. The motor's operating environment should also be considered when selecting a motor. Motors that are operated in harsh environments, such as those with high temperatures, high humidity, or corrosive atmospheres require special enclosures and insulation systems. Motors that are operated in hazardous locations, such as those with explosive gases or dust, require explosion-proof enclosures. The motor's operating environment can significantly affect its lifespan and performance. It is important to select a motor that is designed for the specific operating environment. The motor's maintenance requirements should also be considered when selecting a motor. Some motors require more maintenance than others. For example, motors with sleeve bearings require regular lubrication, while motors with ball bearings do not. The motor's maintenance requirement should be considered when selecting a motor for a particular application. If the motor is difficult to maintain, it may not be a good choice. When dealing with voltage issues, it is important to consider the source impedance of the power supply. Source impedance is the opposition to current flow provided by the power source, such as a transformer or generator. High source impedance can exacerbate voltage drop problems and make it difficult for motors to start and operate properly. When a motor starts, it draws a large inrush of current. This inrush current can cause a significant voltage drop at the motor terminals, especially if the power supply has high source impedance. The voltage drop can reduce the motor's starting torque and make it difficult for the motor to start the load. High source impedance can also cause voltage fluctuations during motor operation. These voltage fluctuations can negatively affect the motor's performance and lifespan. To minimize voltage drop problems, it is important to have a power supply with low source impedance. This can be achieved by using a larger transformer or generator, or by using a dedicated power supply for the motor. It is also important to ensure that the wiring between the power supply and the motor is properly sized to minimize voltage drop. The source impedance of a power supply can be measured using a specialized meter. This meter injects a small current into the power supply and measures the resulting voltage drop. The source impedance is then calculated using Ohm's law, which states that resistance equals voltage divided by current. If the source impedance is too high, it may be necessary to upgrade the power supply or improve the wiring to the motor. High source impedance can also cause problems with other electrical equipment in the system. For example, it can cause lighting to flicker and electronic equipment to malfunction. It is important to address high source impedance problems to ensure the reliable and efficient operation of the entire electrical system. In addition to source impedance, it is also important to consider the power factor of the motor. Power factor is a measure of how efficiently the motor uses the supplied power. A low power factor means that the motor is not using the power efficiently and it is drawing more current than it needs to. A low power factor can cause voltage drop problems and increase energy costs. To improve the power factor of a motor, power factor correction capacitors can be installed. These capacitors provide reactive power to the motor, which reduces the amount of current that the motor draws from the power supply. Power factor correction capacitors can significantly improve the efficiency of a motor and reduce energy costs. They can also help to minimize voltage drop problems. Power factor correction capacitors should be sized and installed by a qualified electrician. It is important to select the correct size capacitors to avoid overcorrection or undercorrection. Overcorrection can cause voltage rise problems, while undercorrection will not provide enough power factor improvement. The power factor of a motor can be measured using a power analyzer. This analyzer measures the voltage, current, and phase angle of the motor. The power factor is then calculated using these measurements. If the power factor is low, power factor correction capacitors should be installed. When troubleshooting motor problems, it is important to use a systematic approach. Start by checking the motor's nameplate to ensure that it is properly rated for the application. Then check the power supply voltage and frequency to ensure that they are within the motor's operating range. Next, check the wiring to the motor to ensure that it is properly sized and connected. Finally, check the motor's mechanical components to ensure that they are in good condition. If the motor is not operating properly, it may be necessary to use a multimeter or other test equipment to diagnose the problem. A multimeter can be used to measure the motor's voltage, current, and resistance. This information can help to identify any electrical problems with the motor. Other test equipment, such as an insulation tester, can be used to check the motor's insulation for damage. If the motor is found to be defective, it should be replaced. It is important to select a replacement motor that is properly rated for the application. The replacement motor should have the same horsepower, voltage, frequency, and enclosure type as the original motor. It should also have the same or better starting torque characteristics. After the replacement motor has been installed, it should be tested to ensure that it is operating properly. The motor's voltage, current, and speed should be checked to ensure that they are within the motor's operating range. The motor's mechanical component should also be checked to ensure that they are in good condition.